All right, hey everybody, we got our second day of the Pythagorean theorem section 6-2 problem set. So you did some of the kind of more introductory problems and hopefully noticed some things with finding some Pythagorean triples and other kinds of patterns that you notice kind of emerged here. So in this second problem set, you definitely get some harder problems. I think there are a couple C-level problems on there. I think 33 and 35 might both be C-level problems. So we'll definitely do that as some of your examples. Also do number 25, which always kind of results in there being questions on how to do it because you're dealing with a three-dimensional figure where you're going to have some right triangles in this three-dimensional figure because you're going to use the Pythagorean theorem within it. So we're going to start with number 25, then we'll move to 33 and 35 after that. 25, you're going to have a few other problems on this because in 25 through 30, the dimensions of a rectangular box are given. So that might be called a rectangular prism, right? In middle school, maybe you're studying three-dimensional solids, and it's just like a box, right? A box that's rectangular. So all these angles that are on here are going to be right angles. If it's rectangular, that's a right angle here. This is a right angle on this side here, and this is a right angle here, right angle here. Yeah, it's kind of hard to see in kind of three dimensions. I don't have a box with me right now. Yeah, I would have had a box out with me so we can like point to the specific parts. Here, maybe this box here. This doesn't really work super well. It's kind of small. Anyways, dimensions rectangular box. So the big thing is the letter D. Okay, the letter D here is something called the diagonal of a prism. And prisms will be defined for you in chapter 10. So that's why they're just calling rectangular box. This is called the diagonal. And we'll just maybe call it the diagonal of the box right now. That's going to be the diagonal going from like this corner right here, which is on the bottom plane, across to this corner that's sort of diagonal, right? So if we think of this as like kind of the bottom plane right here, okay, this is the bottom plane right here. From this corner to this corner would be the diagonal of a rectangle, right? This is the diagonal of a rectangle right here, okay? From this corner here to this corner up top here, kind of on the top plane, that's the diagonal of the solid. So it's sort of running in between the box itself, and it's going to form a right triangle, right? It forms a right triangle right here. So here we have a right triangle UTR, okay? And we're going to have to use that right triangle UTR to get D, because what are we going to know? We're going to know that, for instance, we would know that D squared, because D squared is the hypotenuse, right? This is a diagonal going from the bottom plane here to the top plane here. This is where point R is in your diagram. This is where point U is in the diagram here, and we're connecting them. So that would form a right triangle. Well, if I go down here, that's UT, and then I have RT is the diagonal of the actual bottom plane, right? That rectangular portion of the bottom plane. That's going to be a leg of the right triangle that we have here. So what we're going to know is that D squared equals U squared, okay? And what do we know about U squared? Well, it's going to equal 9. Why? This is a rectangle. We know that opposite sides is a rectangular box. These are all rectangles in this diagram here. So we know that the rectangle UTQ, I don't know, A, we know that opposite sides of a rectangle are congruent because we know parallelograms. Opposite sides of parallelogram are congruent. Rectangles are just parallelograms that have all right angles here. So we know that this is 3. So I know that D squared is going to equal 3 squared plus A squared, okay, right? There's the leg here of this right triangle. This is the right triangle that ultimately I want to get to. Problem is, can you solve this right now? No, that's why this isn't an A-level problem. This is a B-level problem. You can't solve this yet because you have 2 variables in the equation here. You can't solve for D. Ultimately, we want to get the length of the diagonal of the solid, right? That's D I want to solve for. What does D equal? That's my goal. Well, I don't know that yet because I don't know A, what A is here. I don't know why they chose A as a variable, but it's a diagonal of the bottom, right? Bottom rectangle of this diagram here. Okay, anyways, how do you get that? Question is, how do you get that? Well, you got to remember that these are all rectangles in the diagram, so fill about what you don't know. This is a length of 4. That's good. Okay, that's good here. I'm going to mark it up here. 4, where's another length of 4 here? RS is 4. Oh, QT's also got to be 4, right? Because this bottom shape on the bottom plane here, we have defined here is a rectangle. It's a rectangular box after all, okay? So we know that opposite sides of rectangle, because they're parallelograms, right, are congruent to one another. So this is going to be a 4, 6, okay? So we have kind of 2 triangles going on here. So it's very, very difficult to see. So maybe I'll highlight it here. The one in green here is how I derived this formula right here. Okay, that's the one in green. D squared is the hypotenuse, or the square of the hypotenuse, right? The square of the hypotenuse equals the sum of the lengths of the squares of the legs. Well, I have one leg of 3, another leg of A, right? 3 squared plus A squared, okay? Before that, we got to figure out what A is. So I'm going to use this, right? This pink right triangle. This is a right triangle. It's a freaking rectangle down here. We know that rectangles form right angles. So their diagonals would form a right triangle because the diagonal would, whoop, we have a right angle in the triangle, boom, right triangle right there. So what we're going to know is that a squared, all of a sudden here in this pink formula, we can deduce that a squared, because a is the hypotenuse of this pink triangle down here in the base here, a squared has to equal 4 squared plus 6 squared, okay, right? QR squared plus QT squared. Those are the legs of triangle TQR. And TR is the hypotenuse with length of A, so A squared is going to equal the sum of the lengths of those two squareds here. Okay, so that is the pink triangle. Okay, so in these problems here, got to use that triangle to figure out what A is. And then once you have A, use this green triangle here in Pythagorean theorem. So you use Pythagorean theorem twice, right? Once we know what A is, we can solve for it over here. Okay, let's solve for A. A is simply the one unknown here in this equation. We know that the two legs are 4 and 6. So deep breaths, we'll be able to figure out what A is here. Let's go ahead and solve it. So we can square it up, right? We got to figure out what A is. So let's figure out first what A squared must represent. 4 squared is 16. 36, right, would be 6 squared. So there's 36. So A squared equals 52. And yes, 4 would go into that. Here, I use my trick here. Does 9 go into it? No. 5 plus 2 is 7, not 9. So 9 is not going to go into it. But 4, right, it's an even number. Let's try that. Yeah, 4 goes into 60. So 4 would go into 52. 4 goes into 40, obviously. It's just 3 more than that. So A squared would equal the square root. Well, let's take the square root of both sides here. I should have done that maybe earlier. Square root of A squared would just be A. Okay, square root of 52. Well, we can rewrite 52 in a way that's we can see how we're going to simplify square root of 52. So 52 is simply 4 times by 13. And now I can simplify this square root. Square root of 52 is just the same thing as square root because 52 is just 4 times 13 in disguise. Square root of 4 is 2. And we'd have a root 13 there, equivalent to square root of 52. And there we go. We got 2 root 13 is what A is going to be. Now we got to get D, okay? All these questions are not going to take this long, guys. You're just watching this video, seeing how to do it with me, and then, hey, see how you can solve this in just a couple minutes, right? I try to say more than needs to be said to buy you some time and to anticipate things maybe you're not seeing and try to explain them to you. A is 2 root 13, so we can use this formula, okay? Again, this is the green triangle right here. What do we know about the hypotenuse? Well, we don't know anything yet. That's D squared. What do we know about the legs? Well, it's 3. And instead of A here, we just solve for A. It's 2 root 13. So 3 squared is 9. And we're going to do plus A squared. And we substitute that in the value of A is 2 root 13. That's being squared. Okay, nice. We have a root there. So that's going to become 13. 2 squared is 4, though, right? 2 squared is 4, though. So this is going to be 9 plus 4 times by 13. What is that? It's 52 again. So maybe I didn't need to change this from square root of 52 to simplify radical form because I'm just undoing that here, getting a 52. So 9 plus 52, well, that's going to be D squared because ultimately just the final answer needs to be in simplified radical form. So 4 times 13 is 52 plus 9 is 61. And that might be a prime number. Let's see here. 3 doesn't go into it because 3 goes into 60, not 61. Let's see. 9 definitely doesn't go into it. 4 doesn't go into it because 4 is an even number. 25 is not going to go into it. 36 not. So we can't simplify this one. So let's make sure I got the right answer to this because D I got as the square root of 61. Fingers crossed. Oh, wait. No, am I doing this one? Wait, I just did what the diagram was here. Guys, I didn't do 25. Oh, no. It's going to be a much longer video, I guess. I did the example. Yeah, I did the example, guys. You're only getting the example for this one, I guess. Okay, D equals the square root of 61. All right, I'm going to film another video for number 25. Apologies, I just did the example one. Answer here is square root of 61. They write out the whole example for you in the book, so hopefully you get it now after watching this here. All right, I'll film another video with numbers 25, 33, and 35 for real this time. All right, thank you for watching them. Bye.